Okay, let's start again. Good morning, everybody. Welcome to the last day of this wonderful conference. And we can start immediately with Filippo Bracci from the University of Rome Tor Vergata, who he has just changed his title, so you can read it there, The Danger Wall Theorem in Simply Connected Domains. Please.
Thank you very much, Marco. Can you hear me? Yes. Okay. So first of all, I wish to thank the organizers for giving me the opportunity to be here. And well, the reason why I changed the title of the talk is because, you know, sometimes there is kind of sliding doors in the past. So you have some topics and then you change, you do something else, but then you go back to this kind of first lover, and then you say, well, maybe it's more interesting to talk about this than the other. And then, okay, but the reason why I want to talk of this subject is because this is a kind of question that I was asked, and I asked myself several times. It's a kind of curiosity. So, but then when we start thinking, and it's a work in progress with Anna Miriam Benini, and so when we start thinking about this problem, we realize that in fact there are something interesting apart from being a curiosity. So what is the Danger-Wolf theorem? Danger-Wolf theorem, probably you all know, you keep the unit disk, and then assume that you have a holomorphic self-map from the unit disk into itself, and suppose that there is no fixed point inside. So that will be the general hypothesis of all my talk. So this means that for every z in the unit disk, then f of z is different from z. So there are no fixed point. And then it's well known, there is this theorem which was done by Denjoy and Wolf, essentially by the same time, although not in common, that there exists a unique point on the boundary of the disk such that the sequence of iterate of the function converge, let me write like this, uniformly on compact to the point tau, which is the Danger-Wolf point of the self-map. So it means that when you start iterates, if your map has no fixed point inside, then the orbit would converge to a point on the boundary. Now, well, this theorem is not really a theorem about holomorphicity, not even about the disk. And in fact, in general, if you have Gromov hyperbolic metric space and non-expansive maps, then you can always find something similar. Well, here there is a slightly more part, which is the fact that having no fixed point means that the orbit would diverge to infinity. But provided you keep this hypothesis, then in a Gromov hyperbolic space, you can prove that there is a point in the Gromov boundary where the sequence of iterate converge in the Gromov topology to this point. Which, okay, is nice, but then you might say, well, when does this theorem fails? One simple example in C2 is the bidisk. If you keep the bidisk, you can easily construct example where the Danger-Wolf theorem doesn't hold. But however, even in dimension 1, if you keep a simply connected domain. So probably the simplest example is this one. You keep a square, you start removing stuff like this. So you keep on cutting this. And then you continue this way, so everything cluster here. So now what happens is that if you are a little bit familiar with the Caretto-Dori-Primans theory, if you keep the null chain like this one, then all these null chain are equivalent. And you see that the principal part is this part here, the yellow one, while the impression of this null chain is going to be the entire part here. And now what happens is that the Riemann mapping by Caretto-Dori extension theorem, in this case, has a continuous extension everywhere at the disk, except at one point, where this point, the map has the radial cluster set is going to be this part here. And so now if you keep any holomorphic self-map of the disk, like maybe just simply something which squeeze everything to this point, like radially, like an hyperbolic automorphism, for instance, or even a linear fractional transformation, then if you look the dynamics here, well, this dynamics makes in such a way that everything now goes to this. So there is no Danger-Wolf theorem. And that's a kind of example which I think you can even find on Milnor's book, I think. But then the question is, okay, but if I give you a simply connected domain, when do you have a danger-Wolf theorem or when you don't have? Each is continuous up to the boundary, which happens exactly if and only if the boundary of the domain is locally connected, then even in this picture, the orbit converges to one point, which is exactly the image of this point here. So if the domain is locally connected, you say, well, that's trivial. Now the question is, this domain here is very far from being locally connected. That one, I mean, if you keep a convex domain, let's say, or any locally connected domain, then you have danger-Wolf. But is this really the condition, one of the two? Well, in fact, no. The condition is the following. I'm going to state the theorem and maybe give some idea of the proof. So we keep D a domain in C, which is, let's say, different from C, which is simply connected. And yeah, simply connected. And well, if the domain is unbounded, you might consider the boundary in the Riemann sphere. So if you don't want to consider this, just keep the domain bounded. It doesn't make any difference. So the following are equivalent. The first condition is that domain D satisfy, let's say, the danger-Wolf theorem. Which means that if you keep any holomorphic self-map of the domain without fixed point inside the domain, and you start iterating, then everything converges to exactly one point to the boundary. So in this sense, exactly like in the unit disk. And I'll say that the domain satisfies this because this means for every map. The second condition is that and in fact, you just need what I call parabolic automorphism of D satisfy the danger-Wolf theorem. That is to say that if you want to check for every map, in fact, it's enough to check for automorphism of the simply connected domain. If all your automorphism, and in fact, it's enough to consider parabolic, automorphism of the domain satisfy the danger-Wolf theorem hypothesis condition, so that the orbit, they do converge to one point, then it's the same for this map. The third condition is an analytic condition that I mean, this is also a question for you because I never really saw this condition, which is the following. You have, when you do geometric function theory, you study univalent mapping. There are two kind of limits that play really a strong role. One is the so-called non-tangential limit. And or for univalent mapping, this is equivalent also to radial limit. In fact, to the class of any function in the Neval-Linus class, radial and non-tangential limit are essentially the same. Which means what? Which means that if you have a map, let's say F from the unit disk into C, then non-tangential limit somewhere means that you consider all sequences which converge inside an angle going to this point. And then you say that the map has non-tangential limit L if whenever you keep a sequence converging inside an angle here, the limit is L. Or you have the unrestricted limit. So unrestricted limit means that your function, whenever you go to this point, the limit exists. And why these two limits are also, I mean, natural in a sense, because for Riemann mapping, for univalent mapping, Karatudori theory tells that the radial or non-tangential limit are related, in fact, are in correspondence with the principal part of prime ends. While the unrestricted limit, these are related to the impression of prime ends. that is to say, a prime end is an equivalence class of null chain, so-called null chain. So null chain is just, they are Jordan arcs, which have the property that the spherical diameter tend to 0. And each one, let's say you start from 1, which is the first one. And then the next one, then you can define an interior part. And then you want the other part to be contained in the interior. And then the principal part can be defined as the set of convergence of null chains. So in the, I cancel, okay, in the first example, I picture here the principal part is a segment, while the impression is the intersection of the closure in the Riemann sphere of the interior part of each null chain. So these are geometric objects from which you can really see how your Riemann mapping behaves, and they are related to this. However, none of these two conditions is the one which is good for Denjoy-Wolf. The condition is the following. You consider any, in fact, there is one up to precomposing with automorphism, Riemann mapping from D to D. This is a Riemann mapping. And then you want that this map here, H, has what I call H limit at every point sigma on the boundary of the disk. So what is this H limit? This H limit is a condition which is in between non-tangential and unrestricted limit. That is to say, you do have, this is the unit disk. So in the unit disk, you know that, okay, we have a non-tangential region, so it's something like this, unrestricted limit, which is everything. And then you have orospheres here. Orospheres are disk inside the unit disk tangent to the point that you are looking at. So when I say that the map has an H limit, I mean that whenever you have a sequence which converges to the boundary point, even tangentially, but inside an orosphere, then the limit exists. So non-tangential limit is less than orosphere limit, which is less than having the full limit. If you want to visualize it better, instead of using the unit disk, you can consider the right-half plane. In the right-half plane, so it's you use the Cayley transform to move to the right-half plane instead of considering the disk. And what you do have is the following. In the right-half plane, the non-tangential region, let's say at infinity, are just angle which goes up like this. The H limit means that whenever you cut here with some real part positive, and you keep any sequence which goes to infinity, but inside this, then the limit exists. So of course, this is more than the other. And the condition for the theorem is exactly this, that the Riemann mapping, if you want to have every holomorphic self-map without fixed point of a simply connected domain as Denjoy-Wolf point, so the orbit converges to exactly one point, if and only if the Riemann mapping has H limit at every point on the boundary. And this is quite curious because that's condition H limit is rather strange. And well, and then there is another condition, but maybe I won't have much time to describe, is that the fourth condition is that every so-called Boosman orosphere intersect, let's say the closure of every Boosman orosphere intersect the boundary of the domain at exactly one point. So these are the equivalent conditions. And the Boosman orosphere, okay, I don't want to be too technical because I prefer to focus mostly on some example than the proof, which is, I mean, the proof turns out to be much simpler than constructing an example, but let's see. So orosphere in the disk are this guy like this. Now, in this case, for instance, if this is the point 1, then an horosphere is something like, well, you keep essentially it's the sub-level set of the Poisson kernel. So it's something like 1 minus z square, maybe, divided by 1 minus z square, less than some r. So this set here, when you keep r greater or equal than 1, I think, is going to be this set here. And now you can rephrase this in using the Poincaré distance. So this becomes a limit. And in fact, you can keep any sequence, but for when you want to move to some other domain, which is not the disk, what you really can keep is just the invariant distance, something that you can see from inside. Maybe the other way around. So maybe it's bigger than 1 over r. Yeah, thank you. And yeah, in fact, I never remember this formula, but what is simpler is the formula. You keep the distance in the unit disk, and then you consider z gamma, let's say r, minus the distance from gamma 0 to gamma r, and you look for this quantity when the limit converge to infinity, let's say for this guy less than r, or maybe not the same r as before, some m. And now this expression here, where when gamma is a geodesic for the Poincaré distance, so for instance, in the unit disk, you can just keep a radial segment, which comes from the origin, let's say goes to 1. And then if you write this difference here, and you keep the limit exists, because it's the so-called Boosman horosphere, because here you are using a geodesic, so you can see that this function here in terms of t is non-decreasing or non-increasing, and then is monotone, and then the limit exists. And then when this in this way, you can see that this expression here is going to be this one, but this one, when you move to a simply connected domain via the Riemann mapping, it becomes the same. I mean, you just, instead of writing the disk here, you keep you write d, which is holomorphic to the unit disk, and then you get the same expression. And then the condition here is that equivalently, this guy here inside the domain D, they touch the boundary at only 1 point. So that's these are the equivalence condition, the equivalent condition that we found. And the proof, as I told you, is not particularly complicated, because the main idea is why, if you, at the first look, you might say, well, okay, if I do have in the unit disk a map without fixed point, and then I have the Dangerous point, there is the Julia's lemma, which tells us that every horosphere is mapping to itself. So what does it mean? It means that if I keep an horosphere and I keep any point here, then when I iterate, I never can go outside this. And then if I know that the horosphere touch the boundary at just 1 point, then the orbit should go to this point. So that's clear why this condition here is equivalent to have a Dangerous point, morally, because, well, essentially because these are the horosphere. Why the connection with automorphism? This apparently might be the first that when we discover was the one who say, well, that's kind of interesting, because if you what you do is the following, and that's also the reason why you have this H limit. Because if you look in the right half-plane model of the disk, and then you consider now you have your Riemann mapping, and you consider the point which corresponds to infinity, or the prime end which corresponds to infinity using the Riemann mapping. Now, if you do have, you keep an horosphere. So if your map has in the right half plane Dangerous point at infinity, as I said before, this means that this horosphere, which is a real part of z greater than some x naught, is mapping to itself. So whenever we can prove that the Riemann mapping has limit on this line, when you go to infinity, then you win. Because then, I mean, whenever you stay here inside, you know that you go to infinity. And if you have limit here, this a Jordan, when you look to with your univalent function, this becomes a Jordan curve inside the domain, which touch the domain at only 1 point whenever you can prove that the limit on this direction and this direction to infinity is the same. So whenever you stay here and you go to infinity, you have to go to exactly to that point. That's how you prove that whenever you have H limit, you have also the Danger-Wolf point. And then what you do here, the point is that if you consider is a very special family here, which is the family of parabolic automorphism, something of this form, plus, let's say, I. So when the one which move like this, we jump in this way. And then what I claim is that if this guy, when you look into the simply connected domain, converge to something, so the orbit here exists, then, okay, this does not really quite prove that you have a limit along the curve. Why? Because you have a limit along the sequence. And maybe you remember the classical Lindelof theorem, which tells that whenever you have a limit along a curve, then you gain some limit, like non-tangential limit or something like that. But in fact, here the metric of the right-half plane or the disk, since they are convex, is a convex metric. So this means that whenever you keep this sequence and you know that the sequence has a limit, you are assuming that the parabolic automorphism has limit. So you know that here you have a limit. What you can do, you can say, well, I consider this curve here now. I add the missing part. But now the distance from a point here to this point is less than the distance, the maximum between this and this. So in other words, if you want to understand the behavior here, since the metric is convex, it's enough to know the metric on these 2 points. But here you know the behavior, and then along this curve, you get that the limit exists. And once you have the limit on this direction, then clearly, I mean, you have also limit, let's say, along the real axis by the classical Lindelof, and then you can do the same on the other side. And since here the limit is the same, then you get limit here and here. So that's why parabolic automorphism are enough for proving this. And you can even define parabolic, here I went to the core of the idea, but you can define parabolic using intrinsic metric just by considering the steps, the hyperbolic step of the map, essentially. Okay, so this is the idea of the theorem. And now, what I found most interesting are those questions, this question here, that yeah, here we have H limit. And as I said, this H limit implies non-tangential limit, and it's implied by unrestricted limit. Now, the natural question is, okay, you can prove this theorem with H limit, but do you have an example of something where you have H limit, but not unrestricted limit? Yes, in fact, we have. And by the way, okay, here, I don't want to enter into this notion. There is a notion which have been defined some years ago, also by myself and some colleagues, especially in people working in several complex variables like Andy Zimmer, Gautam Barali, and Pascal Thomas, of so-called visibility, which is a notion related to Gromov hyperbolicity, but in dimension 1 is also equivalent to, I mean, to the boundary of your simply connected domain to be locally connected. And visibility implies Danger-Wolf theorem. So if you don't know what visibility is, I'm not going to tell, maybe you can ask later. But what I'm going to say is that with this example that I'm going to explain now, it's also an example of a domain where you have a Danger-Wolf theorem, but it's not visible. So it gives a counterexample to some kind of conjecture that we had. The conjecture might be true for convex domain in higher dimension. Anyhow. Okay, so what you can do is the following. You keep a square. And now, let's say I want to keep the domain symmetric just for, but this is not really an issue, but just for simplifying. So here is the square. This guy here is 1, I think, -1, and this is 1. So this is 0. And now what I do, I keep a sequence, any sequence here of points converging to 0. Here is 0. And I do symmetrically on the other side. And now I remove this slit, radial slit coming here in this way. So now what you see, and of course here they are clustering, no? They are clustering by construction. I have this sequence converging here. So it's a kind of comb. This is a comb, symmetric comb. So what you see is that the boundary of this domain is good, except that there is only one prime end, which the one whose impression is this part here, which has the principal part of every prime end is just 1 point, but there is a null chain, which is in fact this one, that as a tip is this one, so the principal part is this, but the impression is gonna be all this. So it means that the Riemann mapping associated to this one extend continuously, except at 1 point, which correspond to this one, where the map has no tangential limit, but doesn't have unrestricted limit. And what I claim is that this Riemann mapping has H limit. So this domain is not locally connected, but still, if you keep any holomorphic self-map of this domain without fixed point, then the iterates converge to 1 point. And why is that? I just, I mean, that's quite a bit of work. And the idea is, I'm going to zoom there. So the idea is to show that if you keep this kind of horosphere, as I said before, they do touch the boundary only at 1 point. So in particular, the only problem is given by the geodesic. Now I choose this domain symmetric to say, okay, guys, this is a geodesic. Otherwise, you can say that this is a quasi-geodesic and you can do the same work, but it doesn't really matter. So you keep this geodesic, and now you have the geodesic which arrive here. And you want to understand how let me make a zoom of this. So this would be 0. And now here I have my channel, let's say, which is here. And now I have the geodesic, which is coming to this point. And now I fix a point R0, and I want to do, I have what I want to show is that if I keep a point here, I cannot find any sequence inside which belongs to this Boosman horosphere forever. So essentially what I want to say is that if I consider the distance in D between Z, where Z is any point which stay very far away from the enter. I mean, you enter this channel, so you stay very close, let's say here, somewhere. Then this point, when you look to the distance with, I can just take R because this a geodesic. I mean, it's not parameterized by arc length, but it doesn't matter. And minus the distance between R0 and R. This guy here, I want to show that this would explode. So this converge to plus infinity in the sense that whenever Z is sufficiently close to this part here, then you have to take a very large radius of horosphere for having this one. And so whenever Z converges to this point in the impression, you cannot you cannot stay inside the horosphere. And how you do that? Here, the idea is the following. Since we are taking this sequence converging to 0, then the width, we have a kind of semi-strip here. And this semi-strip, the width of this semi-strip is becoming smaller and smaller and smaller. The length is kind of fixed because it's between 1 and 0. And now what you can prove, you need some work, but you can do, is that whenever you have any planar domain and you have inside the domain a strip, then there is a kind of universal constant, which does not depend on the domain on anything, which tells you that whenever, if you cut here, and so you have this constant, let's say D, and then you have to cut something like R, where R is the width of the strip, D, and then something similar on the other side. Then here inside, no matter what your domain is and what is the width of the strip or whatever, the geometry here is the geometry of the strip up to some constant. And what does it mean? In our case, this constant D is universal, but since whenever R tends to 0, because the width tends to 0, then here it means that you cut very close to here, and here you arrive as much as you want here. So it means that now you want to estimate when you come from here, and you have to arrive here. This is your R. So the geodesic, they go from here to here. When it enters this strip, it tends to be the geodesic for the strip. So it tends to to spend most time in the part of the plane where he spent less energy. So he try to stay as far as possible from the boundary. So he morally stay in the middle of the strip. So you get up to here. And now from here, this goes somewhere here. Now here you can estimate, and this distance here is something like, let's say this is morally 1, so it goes like 1 over Rn, where Rn is this part. But now, well, problem is that it's very hard, and we don't know how to estimate directly the distance from here to here minus the distance from here to here. So what we do, in fact, is the following. We say, well, from this guy here, let's say, is less than a constant c, because we are assuming that you stay inside the orosphere. So the first part here, you keep it's greater or equal to something like 1 over r. Oops. Okay, this part. And then you have the other part here that means that 1 over r is less than or equal than the distance from r0 to r minus, you bring on the other side, just the distance from, let's say, this point here, which would be some zeta n or zeta whatever, minus the distance from zeta n and r. And now this, by the triangular inequality, you can kill r. And so you just need to estimate the distance from this point to r0. And this one you can do. I mean, essentially the simplest way is to go like this and then go up. And if you did this estimate, you come up with that on one side you get something 1 over r, and on the other side you have a constant plus some age over r, where age is essentially this part that you need to go outside the strip. Here you are in a good part, but then the rest, when you stay closer to exit, you don't have the same hyperbolic geometry, so you lose this part. Plus, let's say from here to here, which is something like arc, well, sine, hyperbolic sine to the -1 of some r naught divided by r, something like that. So in the end, from here, since r tends to 0, you get a contradiction. That's the way essentially you prove it, because you multiply now by r, and then you get something which is a constant, let's say 1, and here you have something where h is very small, r0 you can keep it very small, and so here on this side you have something which is very small and has to be greater than something equal to 1, and that's a contradiction. So in this way, you get an example of a domain, simply connected domain, which is not locally connected, but for which there always exists the danger point for every self-map of the domain. And now, before I stop, I want to mention that I'm pretty sure that there exists univalent mapping which have a non-tangential limit, but do not have H limit, which will be the final part, because from here I show you that H limit is something really less than having unrestricted limit, but I did not show you that it's not equivalent to have a non-tangential limit. Now, I'm pretty sure that there exists univalent mapping from the unit disk, for which at one point they have a non-tangential limit, but they do not have H limit, because otherwise that would have been in Pomerenke's book. That's that's the reason why I think that's true. But I couldn't find we couldn't find with Miriam. We were thinking. We couldn't find, well, probably it's difficult to find an explicit expression. One might try to mimic in this kind of a result, but instead of keeping channels, something that goes very up like this, so that when you stay here, in fact, you don't spend energy to exit, and then you don't have this kind of estimate. But this is still in progress. Well, I think I might stop here, and thank you very much for your attention.
Okay, thank you. There are common questions, remarks. Okay.
Thank you. That was great. In terms of actual domains, rather than the Riemann mappings, can we say anything about, for example, Fatu components, whether they satisfy this kind of thing? What would you have to prove about a domain to?
Well, actually, that's exactly why we found that this was curious, because if you can prove that the impression at each point is a point, then it's okay. But this means actually that the boundary of your domain is locally connected by Caratodori. So if the principal part at some point is not one point, then you have a counterexample. Then you can create mappings, go in there, and have in such a way that they explode. The right condition is the middle condition, but we do not know. I mean, from it's exactly this H limit. So this H limit, how can you? Because this means that the orosphere, if you think about the orosphere, you have the disk, and then you have the orosphere. And when you keep the orosphere larger and larger, if you consider the Riemann mapping restricted there, they converge to uniformly compacta to your Riemann mapping. So it means that they also, the image Caratodori converge to the image. So it means that every compact set is eventually contained in there. But here you are not really, I mean, the compact set at certain point here, you are inside, but when you move, they are no longer compact. That's why you can lose this. So I don't have, that's a very interesting question. How to characterize, let's say, in terms of Caratodori, look into the picture when you do have a Dangerous-Wolf theorem or not. That's not clear at all.
But for Fatu components, since you have F extending continuously to the boundary, you kind of prove a Dangerous-Wolf theorem, right? I mean, when you prove that for every invariant Fatu component, you either go to a center or to a point on the boundary because you're in a parabolic situation, etc. That's kind of a Dangerous-Wolf theorem, just using the special thing that F extends continuously to the boundary. I would say, yeah, maybe I'm wrong.
You
but...
only.
That's the dynamical condition.
Yeah, for that map, that's what you. Yeah, no, disagree. I mean, I'm not.
Yeah. It's not.
I'm saying here. I'm saying that every map.
Okay.
So if you keep a map with certain property, even if your domain does not satisfy this condition, for that map might
exactly.
Yeah, because otherwise I think you can construct even map which extend continuously, but then they do not satisfy this. I guess I should think about that. So there should be some dynamical condition. I agree. Yeah.
Other questions, comments? Yeah.
You know how to construct this.
Okay, let's talk with Jossa. Okay. Well, I have one comment and one question. The comment is that the H limit actually appeared also when studying Julia's lemma, because the condition of
intersection.
Huh?
It's intersection of orospheres. This is for every orosphere.
Yeah.
And Julia is intersection, right?
The condition that appears in the Julia's lemma under some condition implies the system of H limit at that point where you are applying the Julia's lemma, of course. So it's this is just to say that it is something which already appeared in the literature somewhere. So it's not completely, which is a good thing, which means
no,
it is
you're right.
sensible.
No, in fact, if the map is proper, I think Julia's lemma implies that the H limit.
Yeah.
Otherwise, you have to take the intersection of orosphere, because if the map is not proper, you might you don't know where you go. But
And the question is the following. It's a sort of very vague question. What your theorem is about is the existence of a limit with respect to the Euclidean compactification of the domain. if you change compactification, the situation can change. Well, there is the silly compactification with just the Alexandrov compactification. And in that case, you always have a stupid Dangerous-Wolf limit, just saying that the orbits are going to the boundary and doesn't matter. Do you have an idea if there is some intermediate compactification so that you always have the Dangerous-Wolf theorem, but it is not just the...
I mean, for simply connected domain, you can keep the Caretodori compactification with the Caretodori topology. So it's the disk essentially. So you have there, or which is equivalent in dimension 1, the Gromov compactification. Because there, I mean, if you consider the Caretodori compactification, essentially you are looking to the disk. So in the disk, you have the Dangerous-Wolf theorem. When you look on the other side, you know that there is a prime end where the sequence of iterates converge in the Caretodori topology to this prime end. But then if you want to look from a Euclidean point of view, it means that you are kind of projecting. But it's not, but there is not that you just associate to the prime end its impression or principal part, but also what is important, you see from here, is the way you arrive. So the way you converge to that point. So.
Okay, so with the Caretodori compactification, you always have the Dangerous-Wolf. Okay. Other questions, comments? No? Then let's thank Filippo again.
Thank you.
So welcome back. The next speaker of today is Jasmine Raisi from the University of Bordeaux. And the title, this time is the same as in the program, is Perturbation of Parabolic Endomorphism in Dimension 2.
Thank you very much. I don't know, did I open it? Yes. Thank you very much, Marco. Well, I have to say I'm a little stressed, okay? So you be nice to me, all right? So before I start, let me thank warmly, again, in front of everybody, all the organizers, and in particular, Carlo, Miriam, and Nuria, and also the financial part that I see over there most. I will not mention for, well, first of all, for inviting me to give a talk, and second of all, for organizing such a wonderful conference. It's a huge pleasure to be here. As I may have mentioned to almost everybody that I met in here, it's such a pleasure to be in my hometown, both personally and mathematically. My best friend over there, well, usually the chairperson is my best friend. And in here is a special best friend because he's my PhD advisor, right? So, well, you know, it's kind of being home again. And this morning I felt like going to an exam again because my mom told me, oh, good luck with your talk. Like she was saying when I was at the university, good luck with your exam. It's like, felt more or less the same. I hope it's going to be okay, all right? So, we'll see. So before I get started with my talk, let me spend 1 minute doing something that one of my co-organizers should have done and he forgot to do. So, well, we are co-organizing with Charles and Thomas. I don't know how to do it in English. It's a very French thing, which is called État de la Recherche. And it's going to be somehow a conference and mostly a school. So we are going to have courses on analytic, algebraic, and arithmetic dynamics. It's going to be from January 20 to 24 in 25. So it's easy to remember. And I wrote here the address of the website. And I have to say, while I was writing it, I was like, this is so difficult to remember. So if you don't remember, yes. So there is a link on Charles' page. And if you don't want to go on the link, whatever, if you need some more information, you just email the one of us and we will eventually answer to you, okay? So, well, so now that the commercial is over, I have 47 minutes to go. All right, so let me go and get started with what I'm going to talk about today. So I'm going to talk about a joint work in progress, but I promised Misha that this paper will go out, not the one like the one with Xavier, who has been on the rails for like 2 years now, and eventually maybe will go out on archive. So this one, I also promised Mathieu. Where is Mathieu? Mathieu, yeah, over there. It's really written down. It's almost done. It's just that we are checking some stuff on perturbation of parabolic endomorphism in dimension 2. And this is the joint work, as I said, in progress with Mathieu, who is over there, and he can correct all the mistakes that I'm going to do on the blackboard. And Lorena, who is not here, so she cannot correct me, and she's in Spain, Lorena Lopez. So what we're interested in, oh yeah, before I forgot to mention, please feel free to stop me as many times as you want. I'm here to, well, try to communicate to you something. And if you don't understand me, and if you get completely lost, that's not the point, right? So I'll get where I get. You'll see I'll get a statement on the board quite fast, so that in the worst case scenario, at least that statement is there. All right, so what we're interested in is, so we want to understand the dynamics of a map. It's going to be a holomorphic map from C2 to C2. And if you don't like to think what's going to happen, whatever, think about a couple of 2 polynomials in 2 variables, okay? Easy peasy. And I'm going to fix a point. Okay, let's make it simple. I'm going to fix the origin. And I want this map to be tangent to the identity of the origin. So the differential at the origin, it's the identity. And then I have to say one magic word. I don't want to deal with the trivial case. So F is not the identity, because otherwise, if my question is, I want to understand the dynamics of this, well, the identity is something that I understand. Okay, so I don't want the map to be the identity. And so the question is, what's the dynamics near the origin? And since, well, when I got this invitation, they told me, oh, it's a parameter space and etc. And I usually iterate a simple map with no parameters at all, and so on and so forth. But I was able, thanks to Mathieu and Lorena, to pay the price of being here. And what we are interested in our project is we want to understand, actually, the real question is, what happens if I perturb this situation? So for families, oops, of epsilons from C2 to itself, such that F0 is my tangent to identity map. So I'm going to perturb a tangent to identity map, and you know where I'm going, right? Because we are at the end of the conference, and we've been hearing about parabolic implosion. So what I have in mind at the very end of the picture is I would like to do some parabolic implosion, and I would like to prove a parabolic implosion theorem. Okay, and so actually, since I talk too much, I know that. So I'm going to talk a lot, but I have 15 minutes to do it, right? So I'm on stage. So let me give you the statement, and it's going to be very rough and very unclear. Yes. It's going to be, at the end of the day, it's going to be a holomorphic map. So what I want at the end of the day, it's a polynomial endomorphism of C2 that extends to P2. Okay, that's what I want at the end. But it's going to be true if you take a germ, right? Thank you, Charles. Okay, so this is my sporty part, so that I don't have to go running this afternoon. All right, so let me give you a statement, and then it's completely normal that you don't understand most of the words. If you understand everything, well, that's a little too much. Okay, you can get back to sleep. And my goal today is that you stay with me until the very end. Okay, so at the end, I will have a bonus if you stay with me at the end. Okay. All right, so theorem And that's a Storg, Lopez, and myself, and it will appear. So let F be a holomorphic map. So think about polynomial endomorphism. So that Charles is happy. Of C2, tangent to the identity at the origin, which means what I wrote over there. Okay. Okay, now I have to start adding things. At order 2, and you might guess what this means, non-decritical. And I have some people who know what non-decritical is. And with at least 2 characteristic directions. One of which is non-degenerate. All right. And well, I'm going to state it more roughly than in my note, and attracting. And this is not a standard, well, sufficiently attractive, sorry. Then there exists a perturbation of epsilon of f such that if, well, pi over epsilon, well, let me write it like this, n minus pi over epsilon n tends to sigma, a complex number as n goes to infinity, then f epsilon n iterated n times tends to, and guess what, a Lavor's map that I'm going to call L A. So I will have to introduce a repelling Fatou parameterization. I will have also to introduce my map A, and I will have to introduce an attracting an incoming Fatou coordinate. That's tough, huh? And A of X and Y. So I'm not, oh, sorry. Well, I'm going to write it afterwards. So this is going to be X plus sigma, like always. But then I want something which is really two-dimensional this time. And so I will have today what happens in the second coordinate. And to do that, I will have to go to coordinates, and Marco will not be happy with me, but it's okay. So I will have to define who this Q is. And this is uniformly uncompact of the parabolic basing. Of F naught. All right, so this is quite a, so, and I have to also define this. So I underlined all the things that I have to define for you today, quite a lot. But so this is not the statement that we would have loved to have. So we would simply, what I would love to have is, well, I stay at order 3. You don't know what order 3 is yet. I will go back to that, all right? Non-decritical is something that I think we should assume if we work on in here to have, well, actually, this is the generic case. And I would like to say that I take one characteristic direction that you don't know what it is yet, but whatever, just stay with me. So the statement that I would love is I have a non-degenerate characteristic direction, which is attracting. I would like to take out this sufficiently part here. And then I would like to take out all of this and say, for any perturbation, like in dimension 1, f plus epsilon square 0, so the easiest, I get this. And I would love to be able to find a way of writing this Q here in a more intrinsic way, because for now, as you will see in a minute, well, a little more than a minute, okay, you will see that for now, it depends on the coordinates that I'm taking. Okay, that's Q. All right, so if you are completely lost with this statement, totally normal, we're going to work it out. All right. And to work it out, I know that we had a wonderful talk by Matteo yesterday where he talked about what happened in dimension 1, and there was Alex as well. They were explaining to us and reminding us what happens in dimension 1, but Marco was not there. So I'm going to, well, I have to be nice to my PhD advisor. I mean, that's, sorry, for the PhD students, be nice to your PhD advisor. It's always a good thing, okay? He's your best friend, really. At the very beginning, he's the only friend you have. So I have to remind him what happens in dimension 1 and what's the motivation. I will be fast because he's a smart guy, but I have to do it, all right? And in doing so, you will see where we use what from dimension 1 in our result, all right? So in dimension 1, so motivation. So you go to dimension 1, and you know, well, my favorite map, and since I said I would work with polynomials, I will stick to polynomials. Z plus Z2. So this is tangent to identity at the origin at order 2. So the order here, and this is going to be the same in higher dimension, is the first nonlinear term that I encounter here. All right, so in here, you know exactly. So I promised to my friend over there that I will not use the colors because they are not seeable. I mean, it's impossible to see the colors. So I will simply do it somehow. So in here, I have R, IR, and what happens is that you have, well, let me draw it easily, okay? You have an attracting pedal, an attracting basing, and that's the Low-Fatou flower theorem, all right? This is all of us. So what's going to happen is that you know exactly what happens to the dynamics, and there is an attracting direction, which is not going to be the same in higher dimensions. So in here, the orbits are going to converge to the origin tangentially to the attracting direction. This is something that everybody knows in this place, and it's so nice to give a talk to people who know. And then you have a repelling part, which is attracting for the inverse, all right? And so the repelling, when you do local dynamics, and this is why Charles wanted to know, I mean, if you do local dynamics, a repelling pedal is something that you can define if you use the inverse, because otherwise you're just saying that after finitely many steps, you go away, and then what? And then you don't know anything else. So you take the inverse starts like, it's not polynomial, starts like z minus z squared, it reverses everything, and you're going to be attracting for the inverse. So this is my repelling pedal. So I'm going to call it P at, P rep, even if I should call it P incoming and P outcoming, but whatever. And then what we have is that we have a Fatou coordinate, sorry, and this is going to be called phi incoming. Going to see when you semi-conjugate to the translation by 1, and well, what happens is that in here, so you have a repelling Fatou coordinate, but this is not what we want to use. The right thing to use is the inverse. The inverse is going to extend to all of C, so it's a nice map. And so we have the outgoing Fatou reparameterization, and so coming from C. In here, do you see? Sorry, let me open doors and. All right, so we have this. So we know everything we want to know on the dynamics in the neighborhood of the origin. And so if you ask this question, what happens when you perturb? Well, that's not so difficult now because Douady and Lavoie passed in here. So what happens is that if you consider f epsilon z, which is simply z plus z squared plus, and you're going to write epsilon squared because it's easier and you don't have roots in here when you compute the fixed points. So where epsilon is small and real. So for epsilon equal to 0, you know exactly what it is, all right? But for epsilon different from 0, well, you do the math, and I hope I didn't get it wrong. So you compute the fixed point, and you have two fixed points, plus or minus I epsilon. And this is why I put an epsilon squared, all right? Because I don't want square root in here. So I got from my origin, where I had this two tiny whatever, all right? In here I am attracting, in here I go away. And now my origin split in the vertical part, okay? And so you compute so you have I epsilon minus I epsilon. And what happens to the multipliers? So these are fixed points. You compute the multipliers and plus or minus I epsilon. And what happens in here is that, if I'm not wrong, is 1 plus or minus 2 I epsilon. Am I correct? Are you still with me? Okay. And so, well, you see that since epsilon is real, these have modulus bigger than 1. Slightly, but possibly, I mean, epsilon is non-zero, so it's really bigger than 1. And then you do you go in your kitchen and you take an egg beater, all right? And now I cannot use an egg beater without thinking about it. It's awful. So because you see the egg beater, you have this whatever the name in English is, and so they are pushing away points, all right? And so they push away, and so there is this pushing away, and so if you are a little tiny points who are right in here, well, I know, Arnaud, I'm not very precise. I'm sorry about that, but I think you're getting it. So you're a little point when you're far from the origin, but still in an attracting petal. But if your epsilon is small with respect to z, then iterating f epsilon or iterated f naught is the same. I mean, this epsilon doesn't make a big difference. But when you're near the origin, that's the epsilon is kept. So z is kind to me microscopic, and epsilon is doing something. So you're adding an epsilon square, so it's doing something to your orbit. So, and there is that corridor in here that you can cross. I mean, there is no point, there is no zero anymore. There is no origin there. So you can cross. And so what happens? You got pushed away from I epsilon, pushed away from minus I epsilon, and you go through. And so, well, you pass, all right? And then where you're far away from this zone, which is zone 2, which is in the egg beater, and you are still, well, you will have to prove that you are in the repelling petal. And you can again compare with F0. So what I did in here is that I told you more or less how the proof of Labor's theorem goes. So this is, at least in my mind, and I'm going to put the Labor's theorem here, in my mind, how it goes. And this is what we try to do in higher dimension. So let me erase in here and be a little more precise and give you a statement. So what Labor's proved in his theorem, if I'm not mistaken, in 89, was the following. How am I doing? Okay, no, I plenty of time. Plenty of time. Oh my goodness. So you take f epsilon, which is z plus z squared plus epsilon squared. If you like, you can be more precise. You can add higher order terms. The important part is that you understand what happens in here, and then you can deal with the rest. All right? And okay, you take epsilon minus pi over, n minus pi over epsilon n tends to sigma in C as n goes to infinity. I could take subsequences, but for today, let's keep it simple. It's already complicated enough. So what happens is that you take the nth iterate of f epsilon n, and these are going to converge to the Labor's map that was already introduced by Matteo yesterday, which is simply, you're taking, so in the middle, in here, you will translate by sigma. The sigma is more like a 0. So you have this incoming Fatou coordinate, the outcoming Fatou reparametrization, and you translate by sigma. So T sigma of Z is simply Z plus sigma. And so this is the Labor's map of phase sigma. And this happens uniformly on compacta of the parabolic basin. All right? So, sorry, of F naught. It was very clear in my mind, but it was not on the board. So now I'm going to wait hands. I'm not going to write everything on the board, but so this is something that has already been recalled. Marco, how am I doing? Is it okay? Okay. Am I going louder at the end? So in here, this result is already interesting per se. I mean, you know, well, you had a question, so you asked to answer to the question. But we already heard in this conference how powerful the parabolic implosion theorem is. Okay, knowing this, you can do a lot of things. You can prove the discontinuity of the dependence of the Julia set with respect to the parameter and the field Julia set if you're talking about polynomials. So this is already not an easy result, but you can prove it with using Labor's theorem. But you can also prove the existence of Julia sets with positive area, as Xavier and Arnaud did some times ago. Yeah, it feels so old, but it's not so old. I checked. I mean, and you can ask Arnaud if you want more details. You can study the bifurcation locus, as Mitsu has done. I refer to Mitsu. So you go, I mean, I'm going to dispatch you to all the people that who know more than myself on parabolic implosion. And okay, we can also use it in higher dimension to prove the existence of wandering domains. And this has been done, well, not so long ago. And part of the people who did it are in here. And you can ask Han or Mathieu. And then actually Mathieu studied even more with Luca. So I mean, there are techniques from dimension 1 are useful. And so the motivation to try and go to higher dimension is natural. Because imagine what we could do if we had it. All right? So since I'm coming at last, I cannot not say, I mean, I was going to say it, and you know, but you know it already, right? That this has been studied in higher dimension. And as yesterday, Mathieu was saying, where is it? Yes, here. So the question now is, what about dimension 2? I mean, what about higher dimension? But let's stick to dimension 2 where I can still say something. And we will go to dimension 3 another day, all right? In another conference. So what about dimension 2? And actually, so that's a funny story. I wrote down all the dates because these stories are like, so when you read only the publication dates for these papers, it's a mess. So it's a mess. So you don't know who came first, who did what, whatever. So in dimension 2, well, the first idea was to, instead of studying the question that I just erased, so you perturb a tangent identity germ, but for Smiley and Ueda, and so they did it in 2012, I checked, and it got published. So this is published in 17, if I'm not mistaken. I just checked it, and then I can't remember what I wrote. So, okay, right. So it has been published in 2017. So they were studying what Mathieu was recalling yesterday. So semi-parabolic, semi-attracting implosion. So they were having maps from C2 to C2, fixing the origin. And actually, they were dealing with polynomial automorphisms. But if you want to prove this, a generalization of this kind of theorem, their proof goes through, I think. I'm almost sure. I tried to check yesterday, but I was too tired to do it. But I think their proof goes through. Also, if you just take a polynomial endomorphism, which has a semi-attracting, semi-parabolic point. So what I'm saying is that the differential at the origin as well, I cannot not be precise. So the spectrum of the differential is 1 and lambda. Actually, using the notation of Matthew yesterday, it's 1 and a, with modulus of a smaller than 1. Okay, so they prove a Labor's theorem in this case. And as we saw yesterday, sorry, Marco, you were not there. That's your fault. So as we saw yesterday, the problem is, they get something which is one-dimensional. And so with all the difficulties that comes with it. All right. So, and then there was, where am I? Okay, yeah, here. And then Dujardin and Ljubich. So their paper went out in 2013, but got published in 2015. They studied the same case, oh my goodness, in the, so if I'm not mistaken, it's, so you have a restriction on the degree, so you want it to be sufficiently dissipative, or the other way around, what the name is. So you want the Jacobian to be smaller than 1 over d squared, where d is the degree. So modulus of a less than 1 over d squared. And they find tangencies. Again, for the same, oh, sorry, I have to raise it because it's kind of ugly. It's going to be even worse later, but you'll see. You'll see. So let me make a break of doing this. And then, but this again, it was not what I'm interested in. I'm interested in having something two-dimensional and with tangent identity terms. I'm sorry, maps. All right. And so there is this work by Fabrizio in, sorry. So I think it was 2016 and you got published in 2019. All right. So he dealt with the tangent identity case. So he starts with a map, which is tangent identity. And so in here, so F epsilon from C to itself, and F0 is tangent identity at the origin. And so what we are doing, well, the first part of our theorem is to generalize what he did. And so now, oh my goodness, I have 20 minutes. Maybe I will steal you a couple because Filippo gave you more, so I can steal you a couple. So to tell you what he did and what we do, and to compare the two results, I'm going to now kind of go inside, okay? Give you precise statements and go into coordinates. Even if a good statement, I was told when I was in PhD school, a good statement doesn't need to rely on coordinates, but still it's easier to understand for the audience, I think. All right, so before I go on, first of all, are you still with me? It says so, right? Because I'm talking so loud, you cannot sleep. So no, because it's so interesting. But and do you have questions? Because before I dive inside what I'm going to do. Are you good? All right, we're good. So you remember when I started with the motivation, I was saying, okay, we know exactly what happens in the neighborhood of the origin. Guess what? In dimension 2, for tangent identity maps, we don't know. I mean, so this is the easy answer. The less easy answer is we know some, but not yet all. And actually, I'm becoming more and more convinced that we will never know exactly like we do in dimension 1. So what happens in higher dimension? So let me, can I say, sorry, Fabrizio, I'm going to say that this is of special type. Well, actually, the perturbation is special. Because you fix 2 lines and you have a lot of things inside, and I'm going to write your statement later on, okay? So it's not the general case, but we don't have the general case either. So it's kind of slightly more general. All right, so what happens in dimension 2 is that if I now write my map locally at the origin, or actually I write a polynomial for you, all right? So it fixes the origin and it starts like the identity. So, well, let's write it down. So I'm going to write f of x of y, and I'm going to have x and y, the identity, and then I'm going to add. So, well, I have to make some order in my life, and so I'm going to divide and write homogeneous polynomials, okay? So if I want to say what the order is, I'm going to write down the first homogeneous polynomial that I encounter. That's the least order degree, and so on and so forth. So if I'm very, very general, I'm going to write pk. So yes, let's write it like this. X and y, q, k plus 1, x and y, and then plus I order terms. And pk plus 1 and qk plus 1 are homogeneous polynomials of degree k plus 1. All right? And so if you do that, then what happens is that now we're going to be very general. So this has been studied. So in here, now you know what the order is. So I'm going to do like with my students, what's the order in here? The order of tangency. You are not allowed to answer. You're not allowed to answer. You're not allowed to answer. What's the order? This is my order, okay? So the order of f at 0 is this k plus 1, this first nonlinear term that I have, okay? First, with respect to degrees. And in here, so I was hoping to have more time. So I have quarter of time of hour left. So I'm going to go directly to order 2, but these are more general results. And we could, I mean, there is a whole story that I'm putting under the carpet, and nobody, I hope nobody is annoyed by that. So for now, so stick to k equal 1, that is order 2. So I explained to you one word in what I wrote at the beginning. So now we're in here. So I have P2 of xy and Q2 of xy, and I'm going to call this H2, this map. So this is a homogeneous map, and it's going to go to give you a well-defined map on the Riemann sphere, more or less, because it could be that you have some indeterminacy points that are sent to 0. Okay, so remember in the statement that was in this board, we had this notion of characteristic direction. So there is a problem when you go to dimension 2. There is not exactly an analog of an attracting direction. So in dimension 1, you have this attracting direction where you go towards the origin tangentially, all right? But what's a direction in higher dimensions? In dimension 2, a direction is going to be a complex line, right? So you're still allowed to search for invariant line for the dynamics, but these are going to be complex planes in your C2. So this is C2. I know it's kind of schematic, but each of those is going to be a complex plane. So if I was in a product or a skew product case, it would be easier. So in here, let me tell you what a characteristic direction is. So a characteristic direction is a complex line passed into the origin, which is sent to itself by this H2 map. Okay, so what does it mean? A direction is, it's going to be, a direction is P1, sorry, in P1. So this is a point in P1 of C. And what you want, so it's characteristic, F H2 of V, well, I'm going to write it like this, is equal to lambda V for some lambda in C. And so I'm being kind of precise in what I'm saying because it's important, and also because when you send a line into itself, it can be in a non-degenerate way, or it can be in a degenerate way. So you can send the line into itself, but smash everybody to the origin. And this is something that it's highly degenerate. So if lambda, so if lambda is 0, then you call V degenerate. And this is the case we don't want to deal with. And if lambda is non-zero, then you really have a fixed point for your map on P1, and you call it non-degenerate. All right? And once you are here, you can ask a very reasonable question. Can it be that, how many of these directions do you have? How many? Well, you do the math. I mean, to be a characteristic direction, what you need is that, let me write it correctly, y P2xy minus x Q2xy equals 0. Yes, yes, it's correct. And so when you write such an equation, so these had degree 2, so you have a degree 3 equation. So generically, you have three solutions counted with multiplicities. But I have to say generically because it could well be that P2xy Q2xy is a polynomial, well, say x times xy. And if you are in this situation, that everybody is a characteristic direction. And this is the critical case. So this is the critical, meaning that all directions are characteristic, and we don't want to be in that case. And so in our case, I said non-decritical. So we have three characteristic directions counted with multiplicities. All right, so these three lines that I was drawing in here, they were not by chance. And so what happens in here? So if we add that these lines were invariant, so if you could restrict to this invariant line, then you have this complex plane. F restricted to this line is sending it to itself. So it's one-dimensional. Again, tangent to identity. So you're going to have your attracting and repelling situation again. And then what you want to understand is what happens nearby this characteristic direction. All right? And so I'm going to be skippy. You can attach a number to any non-degenerate characteristic direction. And this number tells you whether or not you have contraction nearby the characteristic direction or not. All right? And so V comes not alone. V characteristic direction comes non-degenerate, sorry, comes with a number that I'm going to call alpha V. So this number is a director because it's going to tell you what happens nearby the characteristic direction. And if it's pointing inside, then the points in here are going to smash morally on the characteristic line. And so what happens is that you're going to be able to enlarge these petals like Matteo was doing yesterday, but both of them, right? So in the same characteristic direction, you're going to have two-dimensional parabolic petals and two-dimensional repelling parabolic petals for the inverse, because when you compute the inverse, this map as a homogeneous map on P1 is the same. It changed by a minus. And the directors, then you have to trust me, the directors are the same. So if this is attracting, it's going to stay attracting all over. And so you're going to have two-dimensional flowers. All right, so I'm not citing the right people that I should cite. So let me cite them. So what Kim tells you, I'm super slow, I'm sorry about it, but if you get a meaning of what I'm saying, it's more than something. So Kim, I met Cal before. Let me put him in parentheses. And I will explain you why. So in 1998, I would think, more or less. So what she says is that if the real part of alpha v is positive, then there exists a two-dimensional attracting pedal for F and a two-dimensional repelling one. And I'm pretty sure that she knew that they were going to intersect. But what she does, it's a very local description. So she doesn't care. She just wants to prove that they exist. And they come with two coordinates. So I think, I don't know. I myself always thought, yeah, okay, they will intersect, but I'm too lazy to prove it. But Lorena Lopez and Rudy Rosas, a couple of years ago, they proved that the attracting and repelling pedals and repelling pedal, they do intersect. And you have to picture in mind the same idea that I wrote over there. So in here, what I'm saying is that if I see it in this one-dimensional picture, is kind of a little easier. But what I'm saying is that I'm now forgetting everything what happens outside my for the other two characteristic direction. I'm going to focus in the neighborhood of a characteristic direction. It's already enough. And in here, I have my attracting pedal and the repelling one. And in dimension one, if it was invariant, they would intersect. But in the general case, you don't have only this part. You're going to have more polynomials in here, so they are not invariant anymore, but they leave a shadow of this invariance and not this intersection. And so since you have attraction in here, you can make them both fat. You have these two attracting and repelling guys, and they are intersecting because they are kind of built on these two intersecting pedals. And once you have this intersection, then you might hope to do the same. That happens in dimension one, all right? Except that there is a problem. So the problem that we have, I'm over time. So I'm going to, yes, I will not give you the formula. You will have to invite me again, and I will show you, or ask me, and then I will write it down for you here. So what happens if you have f epsilon, which is f plus epsilon squared 0, and you want to compute the number of fixed points? But for God's sake, you have two variables. So when you do this, you get 4 fixed points. Haha, what are you going to choose? What are the right fixed points to choose? And so this is why we have, so actually this is not a big deal. So you have 4 fixed points, and then you compute the asymptotics of the fixed points. And what's happening is that I still have 4 minutes, 3. So the asymptotics of the of the fixed points is that there are 2 that are near the origin, and there are other 2 that are kind of far. And so these 2 fixed points that are nearer, you're going to take these ones. And then you would like to have them, because life is already complicated enough, and you have 2 variables, and this for 2 parameterization and for 2 attracting coordinates are difficult to deal with. We have 2 maps this time. All right, so we have to, what these 2 maps are saying, they are telling you what happens in the y variable in here. So how you are converging to the origin. And this is why we need it to be sufficiently attractive, because otherwise it's not working. But it's not a big deal. So once you have this, guys, you would like at least to have these 2 points at plus or minus I epsilon 0. So, okay, so 2 of which are almost at plus or minus I epsilon 0. And so, well, okay, we are allowed to use affine transformations. So we put them at plus or minus I epsilon 0. And again, and now we cross fingers and we hope that everything goes through. So let me give you at least the map that we studied, and then maybe I will call the day with your bonus, because you were a nice public. You stayed with me, so you have a bonus at the end. All right, so where is it? Where is it? Here. So what we have is that we start with fxy, which is of the form x. Oh my goodness, no, I don't want it this way. Yeah, but I have to. Okay, fine. F plus x squared times 1 plus, I have to take care of this term, plus O2 of xy. I would love to stop here. That would be so easy, but I cannot. So I have to add what happens in here. So I have a y variable staying there. And y plus, okay, oh my goodness, x squared c naught of xy plus y times dy plus rho x plus O2. And I was hoping to be able to compute for you and with you the characteristic directions. So you will have to do it yourself. But I have to tell you at least one thing. So when I said we have a perturbation, I know I'm minus 5 seconds. So when I said we have a perturbation, is that we have to prepare our first map before perturbing it. So in here, what I want is to get rid of some terms that are bad when I do my math. And so the terms that are bad are those pure in x. So with no x to the m, for m, let me write it like this, small. Meaning that I can quantify it for you, but I'm not doing it now. All right, so this is kind of x squared multiplying something which is of high degree. Think about it like this. And so now what I'm going to do is f epsilon. So if I'm in this case, it's going to be x squared, well, a epsilon xy plus y b epsilon xy and y plus y times rho x plus dy. This is not really a big deal. Plus O2. Sorry. Whatever. I'm going to write it in this case. And there is an epsilon square in here. Otherwise, nothing is working out well. Sorry. I'm almost done. Promise. Plus y. That's a c. And that's the epsilon xy. All right. And in here, I have to have this row big enough so that big enough means the real part is at least 2. And I know Mathieu doesn't agree with me, but I checked it yesterday. So it's at least 2. So I'm right. But the director is at least 3 of real part. So I promised a bonus. Can I write it at the board? So the bonus is that as the corollary, the small Julia set well, does not move continuously. So if you take the map, so you got a discontinuity for the small Julia set. which is the Julia set that Fabrizio was talking about on Monday. So in higher dimension, you have several Julia sets. And what Fabrizio did with his result was to prove that the big Julia set is not continuous at this epsilon 0. And in here, we managed to get to the small Julia set, which is the one defined at the support, like the support of the measure of maximal entropy. But I'm over time of 3 minutes. And so I'm not indulged anymore with my stuff in here. If you have any questions, please feel free to ask. Thank you very much.
Thank you. There are, yes, better questions. Okay.
So instead of considering the maps tangent to identity, can you consider the vector field and the bifurcation? Is it already studied by somebody?
I think, so I cannot answer if it's been already studied because I didn't check. So it might, but I'm not sure. And I don't see why we could not use vector fields. I mean, we didn't do it because life was already difficult enough in here, but maybe it may actually be easier.
Yeah, vector field may be easier than the maps tangent to identity.
Yes, exactly. So what you are seeing, and it's so nice that you're here, is that how do we construct the approximate? Sorry, I'm really being very precise. So you need the approximate for 2 coordinates, and the approximate ones, we get to them using vector fields. So we are integrating a vector field. And that's why so I would say that the vector field case should be easier than what we're doing. But for some reason, we want to work with polynomial endomorphisms. So in here, you get the discontinuity in the family of polynomial endomorphisms. And so, well, if you want to deal with that, you have to leave out the vector fields. But that's a very good question. And I'm glad
The
you asked.
situation may be simpler. So
Yeah, it is
that's
kind
why
of.
I'm.
Yeah, thank you.
Okay, thank you.
Other question? Yes.
I understand this is two-dimensional complex but local theory. Many years ago, I was interested in two-dimensional real but global. And a long time ago, there was a famous paper by Newhouse, Pallis, and Takens. It was about cycle feather nodes. Strong one-dimensional unstable intersects weak two-dimensional stable. There is a vibration invariant if it is in one parameter family, etc. And it has been famous paper because when you push and there is a cycle, you obtain a non-homomorphism, a continuous mapping in the limit for your n tending to infinity, mapping of the circle, but not invertible, and rotation interval was introduced in this famous paper. Is such a global theory would be interesting because it is already locally very interesting and globally even more interesting.
It is surely interesting. And we have not dived into that. We might. Thank you very much for your question. Look.
So I have 2 questions. So first one is just, can you sort of compare? So what's the main difference between your result and what Bianchi had? I think if I remember correctly, he also has this continuity of Julia sets, except for being more less special type of map. And the second one, is I guess so you're working with a fairly general type of maps. So as you know, you could sort of also add up some nice tail to make this automorphism.
Oh yeah.
Right. So I guess does that hold in for those maps as well? And would you expect then this Lavor's map to be injective in that case?
Yeah, okay. So let me go first. First things first. So I was planning to compare with Fabrizio, but I didn't manage because I was too slow. So Fabrizio, what he did, So he knew that in his paper, you will not find a two-dimensional attracting Fatou coordinate and so on and so forth, but not because he doesn't know that they are there, because he doesn't need them. So he wants to prove the discontinuity. I mean, he's here, he could answer, but yes. So he wants to prove a parabolic implosion results. And so what he does, for example, he fixes two lines. And so he has a nice structure that we don't have. So he has these two lines where there are fixed. And then what he has, so he doesn't have the uniqueness of the limit. So he has normality, and then he has that if you take any limit map in the neighborhood on where he's working, so in the neighborhood of this invariant line where you have this it's not over there anymore. So when you have the one-dimensional attracting pedal, then you have the Lavor's map. So he proves a very nice result, but it's not, so you have normality, but you're not taking the full limits on all of the basin. And that's kind of stronger. So in his case also, he only has two characteristic directions, one of which is non-degenerate, the other one is degenerate, and I would say double, because otherwise we're not in the right multiplicities. Our statement works for two, well, his case, and the generic case where you have three. I have to be honest, so he has a little, so there is a little difference in the form of the map that he's taken. There is an RY in the first coordinate that we can't get here, but we could add. It's just that we didn't want it for the moment. And in his case, he has less problems with the real part of the director. And so he has the real part of rho is bigger than 1. And for us, for the moment, we have it bigger than 2. And if I'm not mistaken, we could make it bigger than 7/4. But, you know, it's kind of not optimal yet. And what was your second question? Oh, yes, you can get it for automorphisms that are not polynomial in C2. As soon as you fix your, say, jet sufficiently high, and it's actually sufficiently high, it's not so high anymore, much, and you add, and you make it an automorphism. It's just that for the moment, it's not written down. So I think we might do it. Like, yeah, of course, you want it to be 1-to-1. You want well, it's an automorphism, so. You can, I mean, if you start with the identity and you make it invertible, and then you know that you can use Anderson-Lampert theory to extend it, to find an automorphism that has the same jet. Yeah, the tail is not so important. It's kind of a pain in your neck, but it's not so important. But thanks for asking.
Okay, let's thank Jasmine again. Okay, we are at the end, and the end of a very good conference should be an excellent talk. So I'm very pleased to introduce, where are you? Misha Ljubich from Stony Brook, who is going to talk about a priori bounds in the quadratic family.
Thank you, Marco. So now I feel responsibility. All right, well, thanks for inviting me. So it's a big pleasure to be back to this city, to Pisa. So I was here like 10 years ago, more than 10 years ago, and kind of it's really a pleasure to visit again this kind of legendary scientific center. Well, so I will be talking on a priori bounds for the quadratic family. It is kind of technical talk. That was my idea, that the audience is are experts in holomorphic dynamics, and so I don't need to do general talks. So we'll try to be slightly more technical. And so it could sound very technical, a priori bounds, but as a matter of fact, it is becoming a kind of central theme in our field, because the renormalization theory, so which has been developed already over 30 years and very successfully, so it's now very well understood in general. We basically are in control of all the pieces of the theory, so the scaling, how it affects, so how it is it manifests itself in the dynamical plane, in the parameter plane. So these little copies of the Mandelbrot set, elephants marching from the cusp, so Ziegel disk, self-similarity of Ziegel disk, all these issues which is the subject of normalization theory is now very well understood, but there is one issue which is still not completely resolved, so despite all the efforts, and it is a priori bounds. It is a kind of analytical geometric input to the theory. After modulo this issue, the theory is in our hands. So I think that this a priori bounds matter is becoming more and more important, and I will try to update you where we stand these days as far as I can see it. So, okay, so the conference is about parameter spaces in holomorphic dynamics, and that is, of course, the icon of the parameter space in holomorphic dynamics, so nobody needs any explanation what it is. So for us, it's certainly a very rich set, and whereas people are interested in very little, some specific parts of this set, but there are kind of 4 places associated to the normalization theory, which would be of particular interest for us. So, and of course, everybody recognizes these places. So it is little primitive copies of the Mandelbrot set, little satellite copies of the Mandelbrot set, and they are associated to the quadratic-like renormalization. So here in the parameter space, they can be found here and here. And then we have some parameter, which is a Ziegel rotation number. So, and there is self-similarity, which is less familiar, but still, so self-similarity near the Ziegel parameter, and there is associated normalization theory that explains this self-similarity, and there is very familiar to many people here, and we have heard a lot in this conference. It is this parabolic renormalization theory, and so near parabolic bifurcations associated with this herd of elephants marching from the cusp. And this, by the way, so for my talk, it will be somewhere on the background, but not really, I will not really touch upon it. So this, but this renormalization theories, so will be very important. So quadratic-like renormalization theory and kind of Ziegel type renormalization theory. Okay, so and here are some illustrations. So what this theory is all about, and again, it is kind of familiar. Should be familiar to essentially everybody here. That is quadratic-like renormalization. So, well, renormalization is a rescaled return map. And in the quadratic-like theory, the return map is a quadratic-like map. So we take some disk, it goes around and returns back as a quadratic-like map with connected Julia set. And then the map is called renormalizable. And there is associated combinatorics to this renormalization, so namely, well, period of this renormalization, of course, the most important combinatorial parameter, but also the Hubbard tree of renormalization. Somehow these little Julia sets can be connected by arcs, well, at least in the combinatorial way, by arcs of the Julia set, and then we obtain a Hubbard tree, which records the combinatorics of this renormalization type. And there is a famous, remarkable theory by Doherty and Hubbard, which tells us that the maps which are renormalizable with certain combinatorics, so these parameters form a little copy of the Mandelbrot set. So, well, so that is period 4 combinatorics, so renormalizable maps with period 4. So we go around, and then this returns back as a quadratic-like map, and then the associated little copies of the Mandelbrot set blown up, indistinguishable with the big Mandelbrot set, and that is what renormalization theory explains quite well. And another most famous maybe parameter is the Feigenbaum parameter, classical Feigenbaum associated with the Dublin normalization, and it is satellite type renormalization associated with satellite copies of the Mandelbrot set attached to one to another, and ultimately to the main cardioid of the Mandelbrot set. So that is quadratic-like renormalizations. And we also will be interested today in Siegel type normalizations, just understanding scaling property of Siegel disks and actually beyond Siegel disk, also Kramer points. And this normalization, so it is people already, it's known since late 80s, since it this kind of a priori bounds, quadratic like a priori bounds. So I did not say you what a priori bounds. Let me just introduce this term in this general way. So just if the map is infinitely normalizable, or if the map is infinitely normalizable in certain sense, in the quadratic-like sense, this normalization somehow control the map, at least topologically, in these arbitrary small scales. But topological control is not good enough. So for good theory, we need some geometric control, and ultimately very good geometric control. Ultimately, we want some scaling limits for these normalizations. But a good way to start is to have rough geometric control, some a priori bounds. A priori bounds is rough geometric control of the map in all scales. And as I told you, if we have this, then so essentially we know how to proceed further. Essentially, we know how to proceed further, and there is a very good conditional theory. So not complete, but still there is a very substantial conditional theory modular a priori bounds. And what in particular situations in conformal dynamics, a priori bounds usually mean control of certain conformal moduli, and it could be modular of certain annuli. So for quadratic-like maps, it is fundamental annuli is the most convenient parameter. So, and control which is needed is some uniform lower bound. And it turns out that this just specific parameter controls the rest. So that is very, very strong information. But it was known that in the satellite case, for satellite normalization, it is not valid in general. So maybe it is valid for primitive normalization. Conjecturally, this kind of control is valid for primitive normalizations, but for satellite normalizations, it fails, should be replaced with something. And then there is some other type of normalizations. So there are experts, big experts on this normalization in the room. So, and it is, let us refer this in this talk like sector normalization. So here we consider the return, consider some disk and return map of this disk back to itself as a quadratic-like map. And in the sector normalization, we consider some dynamically defined sector and return map to this sector. But because this map is discontinuous, so the situation, so it would be good to fix the situation so that we deal with continuous maps. And there is a nice way of doing that. I think that originally going back to the idea of Doidias, as I can tell. So, and the way to fix it, to take dynamical sector so that these boundary components are dynamically related and identify them by dynamics. Consider the corresponding quotient Riemann surface or Riemann orbifold, so and uniformize it back, say, by the unit disk, and then we will obtain a similar picture as before. And here is the indication of some Siegel disk, which looks like amoeba for big combinatorics, and we would like to control the Siegel disk in all scales by means of this kind of sector normalization. And this sector normalization, as I already alluded, is kind of more related, it's also very much related to understanding satellite quadratic-like normalization, more related than the quadratic-like normalization. Topologically, for satellite case, we still can define quadratic-like normalization, but it is poorly controlled. Okay, so here is some reminders. So I already used this terminology. But let me remind you that primitive means dynamically that the little Julia sets are pairwise disjoint. So like here we have 4 little Julia sets and they are pairwise disjoint, and satellite means that the little Julia set can touch at some particular fixed or periodic, more generally majority point, and it is reflected by the corresponding Mandelbrot sets. So primitive Mandelbrot sets have cusps. They come from nowhere, or rather from saddle node bifurcation, and satellite Mandelbrot sets, they come from the satellite bifurcation. They attached to some other hyperbolic component of the Mandelbrot set, and they don't have cusps. So easily distinguishable normalizations if you look at the picture. And I will also use terminology Feigenbaum maps. It is infinitely normalizable quadratic-like maps of bounded type. So bounded types means all relative periods of renormalizations are uniformly bounded. But I will be interested not only in bounded type renormalizations, but also in unbounded type. Okay, that is setting kind of the stage. So, and we are interested in a priori bounds today. And as I told you, all the scalings that we see on the pictures would naturally follow. So it is already non-trivial, deep, but available theorem, modular a priori bounds. Yeah, also, of course, I should have mentioned that rigidity type questions. I should have started with this rigidity type questions, which is a question equivalent to the local connectivity of the Mandelbrot set, the MLC conjecture, also essentially reduced to a priori bounds. At least we understand how to proceed. There is no formal theorem saying from a priori bounds we can go to MLC and rigidity, but there is clear understanding how to do it once a priori bounds are done. Okay, and so now let me sort of pass to some more technical stuff, more technical part. So how one can approach a priori bounds? There are various approaches. So in the 90s, for instance, a priori bounds were approached through the Yakos puzzle machinery. So, and I had some results in this direction, so which were sufficient to understand quite well the dynamics on the real line. So, or they could be approached by some kind of perturbative methods. Say, understand first parabolic parameter, parabolic renormalization, and then perturb it a little bit so that you will understand, say, high type renormalization, high type Ziegel disks. And that is a theory that was developed in the about 15-20 years ago by Mitsu Shishikura and Ina. So this is a machinery that was successfully used to obtain to go to quite interesting results about particular parts of the parameter space. However, so in the about 20 years ago, in the early 2000s, a new machinery was brought to the scene. It is called near degenerate regime. Now we call it this way. It actually came from hyperbolic geometry, so two dynamics through the work of Thurston. And people in this audience very well familiar with the dynamical work of Thurston, which came straight from his hyperbolic geometry intuition. So and essentially you can see from the outline of Thurston's theory what is this near degenerate regime. So you consider iteration in the Teichmüller space, so you have some sequence of Riemann surfaces, and you badly want the Riemann surfaces not to degenerate. And in order to do that, to achieve that, you need to understand very well how they can degenerate. So, and for compact Riemann surfaces of finite type, so it is very well known what can happen with Riemann surfaces. They just can pinch in the modular space. They can just, the only thing that can run, which can happen is they pinch along the closed geodesics. So they pinch along the closed geodesic, and then these closed geodesics, short closed geodesics, become related in some dynamical way, and you can analyze and you can come up with this notion of Thurston abstraction. And so we know how useful and powerful these ideas are. And so now these kind of ideas were brought about 20 years ago to renormalization theory by Jeremy Kahn. And so yeah, I will start with some crucial notions of the setting which is needed for renormalization. For renormalization now, in the certain theory, we needed just Riemann surfaces, compact Riemann surfaces with punctures. So finite type Riemann surfaces. Here, we need Riemann surfaces with border, with boundary, and essentially just disks with several holes, with finitely many holes. That is what we need for normalization. For normalization theory, and these holes, it is just sort of blown up little Julia sets. So inside of some disk, we have some little Julia, for instance. So it can be something else. So, but that is a basic model. So what can happen? What can happen with these Riemann surfaces? How they can degenerate? And it turns out that more important than the degeneration along the closed curves, which will not play any role for us today, but the important type of degeneration is the degeneration along arcs, just arcs, which connect different boundary components of our Riemann surface. It could be just two inner components connected by some arcs, and this arcs could be a sort of combinatorial, very complicated arcs. This picture somehow try to reflect some complexity, or they can connect some inner arc to outer boundary. These ones are called vertical. These ones are called horizontal arcs. And so there are, of course, arcs which can connect vertical to vertical, which also will not be important for us today. Somehow they can be safely ignored. And so degeneration happens along the arc in the following sense. So take some arc, and now let us think of this arc as a simple arc here, because it is difficult to draw what I want to draw for the complicated arc. So, and assume, so you can imagine that there is a very wide rectangle which can be inserted here with 4 vertices on the boundary components. And white, so it can be uniformized by the straight rectangle. So with these 4 vertices corresponding to the corners of the rectangle, and white means that the width over height is bigger than 1, bigger than 2, bigger than millions. So degeneration, when this width goes to infinity, then it means that we degenerate along this particular arcs. And so it turns out that, so if we record all these arcs which all these heavy arcs with heavy weight, so this weight will be the modulus of this rectangle. So in the modulus of the rectangle, or the weight of this rectangle is the horizontal side on my picture over the vertical side. So if we record all the arcs with big height, say bigger than 2, with big weight, bigger than 2, then we obtain finitely many arcs, because they must be disjoint. Turns out that these arcs must be disjoint, so there will be finitely many arcs, like not more than 3p minus 3 arcs, where p is the number of holes here. And these arcs will control the degeneration, or is important for us, is the generation of our Riemann surface. Essentially, if you now consider the whole path families emanating from our inner disks, so outside, and so calculate the total weight, the total width of this path family. For people who are familiar, and of course people are familiar here with the theory of external length, then they understand that this modulus of the rectangle can be expressed in terms of the external length, or rather external width of this vertical family. External width will correspond to the horizontal sign over vertical. Length will be the inverse quantity, vertical over horizontal. But more general, one can define this conformal invariance for general path families, and then the whole path family, or now the whole family of all paths emanating from these little holes, from little Julia sets anywhere, will be controlled up to some bounded error by the sum of the weights, sums of the widths of these degenerating rectangles along the canonical arc diagram, along the family of arcs associated with our rectangles. That is the basic picture of degeneration of Riemann surfaces with boundary disks with several holes, and just it should be kept in mind. It is as important for the normalization theory as degeneration along closed curves for Thurston theory. Okay, so and yeah, so let me mention that so that there are two types of arcs. So horizontal and vertical in the case when we have this disk with the hole, and they play different role. And in particular, you can notice that if you consider the annulus, so just annulus attached to the outer boundary, that this annulus will cross essentially only vertical arcs. So the width of this annulus, so how degenerate this annulus will be fully controlled by the total weight of the vertical arcs. So that is the role of vertical arcs. While if we go around little Julia sets, then here the contribution to the modulus of the corresponding annulus will come from both vertical and horizontal. So you see that they will clearly, because we want somehow to relate modulus of the original map and the modulus of its normalization. So the interplane between vertical and horizontal arcs becomes important. By the way, I most likely will use the notion of modulus of the annulus in the way opposite to what you are familiar with, what you're used to. So in dynamics, we usually call it, say for the straight annulus, it is like log outer radius over the inner radius. And for me, it will be mostly inverse. So somehow the modulus is big would mean that the annulus is very, very thin. So sorry about this confusion. It's kind of canonical confusion. In literature, people in analysis use it traditionally in the opposite way as people in dynamics. But here, analytical terminology is more relevant, more convenient. All right. So, but still, so this, so we will be talking about weights, so sort of widths or weights of the annuli, of the fundamental annula of our quadratic-like maps, and these weights are inverse to the moduli we are used to. It is inverse. So, and so as I told you, we want to control moduli from below, dynamical moduli we want to control from below, meaning that we want to control this width from above. We want to control width from above. So degeneration would mean that the width of our annuli will become big. Near degenerate regime, it means that we are dealing with annuli with big widths, very thin annuli. And Jeremy suggested in this setting, so such a strategy of dealing with the problem of a priori bounds. So we badly want the weights to be bounded from below, assume that they're very big on certain level, then we want to show that they become even bigger, twice bigger, for instance, on several levels up, several normalization levels up. He formulated it as a life improvement principle, so optimistical principle. So if the life is bad here today, then it was even worse, say, n years before. So it is optimism. So in the sense of Jeremy Kahn. So well, so how to do that? So clearly that if you are able to establish this principle, then that's it. That's it, because you can start with quadratic polynomial, for instance, for which there is no degeneracy whatsoever. The fundamental annulus has a big dynamical modulus, infinite dynamical modulus for that matter. So, and if you have this principle, you start with some degeneration here, then you obtain bigger degeneration several levels up, then obtain bigger degeneration several levels up, and so on and so on, going all the way to 0 level and obtain a bigger degeneration for the quadratic family, which is not the case. For the quadratic family, it is not degenerate situation. So there will be a contradiction. So that is the strategy to how one can do it. And here is more specifically how the strategy was realized. So somehow, so yeah. So as I mentioned, so we need a lot of verticals. So we have some big modulus here. We have a big modulus, a big weight here, and we want even bigger weight here. And this bigger weight is controlled by the weights of vertical arcs. So we want, for this strategy, we want a vertical arcs to have big weight, So how it can be done? So, and here is the idea. So we can start dynamically restrict the domain of our map, just taking the pre-images, restrictions the domain. And when we restrict the domain, then some of the horizontal arcs will start hit new boundary and breaks, and will start breaking into vertical arcs. So we create we lose horizontal weight, and we create a vertical weight when we restrict the domain. And it turns out that after several restrictions, not so many restrictions, but several periods of our normalization, like 3 periods of our normalization, after these restrictions, we can create a lot of vertical weight compared with the horizontal weight. Okay, so, and that is actually the moment, that is an important moment where primitive renormalization plays the role. So where primitive renormalization plays the role, because what is needed here about primitive renormalization is that the dynamics on the Hubbard tree has positive entropy. So dynamics on it is a feature of the primitive renormalization. And when dynamics on the Hubbard tree plays has positive entropy, then after restriction, so if we take some restricted rectangle, horizontal rectangle, it can be kind of concatenated by several pullbacks of the original horizontal rectangles. And so the weight of this restricted rectangle by the series law, which is called Grothin equality in dynamics. So if we assume that this is 1, then this will be 1/2. So the length will be at least twice bigger than the length of each of these, and the width, which is inverse to the length, will be twice smaller than the width of that. So if we can concatenate arcs with the pullbacks of the original arcs, then we lose weight. And so if the entropy is positive, we can do this with every horizontal arc, and so the whole horizontal weight can be lost somehow or reduced in this way, given some vertical weight in return. So that is the first step. We restrict the domain, and we trade in the horizontal weight to the vertical weight, which is good, but it means that we estimate modulus. We see big modulus, but only after 3p restrictions. Only after 3p restrictions, that where p is the period of our normalization. So, well, we want to return back to the original domain. The period can be big, and actually should be selected to be quite big, even in the bounded case. So P is the number. So P is the period of this normalization. And we should think of this normalization, maybe not the first normalization, but maybe we skip several. So even if it is original was tripling, then it could be 3 to the power 100. So it is, we should think that there are many bounded number, but many of these guys. And then we restrict 3p times. So 100, 3 to the 100 times, 3 to the 100 times. So restrict, we just take the full pre-image of our domain. So we have a, so you have the domain U of quadratic-like map, the range. You take the next domain, etc. And you just restrict these domains. Just restrict these domains and just look at the diagrams of the restricted domains. And diagrams of the restricted domains come from these diagrams just by the breaking the corresponding families, roughly speaking. So the horizontal families in particular can become vertical. So if the boundary goes like that, so you have some horizontal line in the original domain, but horizontal arc in the original domain, but it becomes two vertical lines, two vertical arcs in the restricted domain. And so we lose horizontal weight, we gain vertical weight. But we gain vertical weight on the restricted domain. It can be many restrictions, 3p is a big number. And then we have to come back somehow in the way which is independent on p, but depends only on the way of depends only on the combinatorics of renormalization, and this can be done by means of the covering lemma that we developed with Jeremy together at that time. And this covering lemma allows one to push forward big weight. It is specifically lemma for near-degenerate regime. So it is transformation rule, some transformation rule for the moduli, of certain annuli, which are almost degenerate. So and here it says that, so we have like 3 domains here, most importantly two domains, lambda and u, and there is some color here. Just neglect color for the moment. 2 domains, this annulus and another annulus. And we have a map of big degree from outer domain to this outer domain, which restricts to the map of a small degree, little d, from lambda to lambda prime. And we want the weight to be pushed. So from here, if this annulus is degenerate, then this annulus will be even more degenerate with some constant, or not even more degenerate, but comparably degenerate, with some constant that depends only on little d. So that is the point of this lemma, that the weight can be pushed in the near degenerate regime. In this situation, weight can be pushed with a constant depending only on the little degree, if we forget about the issue of colors, which is a kind of technically important issue, but to the first approximation, let us disregard it. And what depends on the big degree is only the level of degeneration, only how degenerate this annulus should be. And this exactly allows us now to push the weight from the restricted, now we dynamically push the weight from the restricted domain to the restricted Riemann surface to a bigger Riemann surface. It will be big D. Big D will be like 3 to be like so we have 3p, so will be like 2 to the power 2p or something like that, and small d will be like 2 to the power 3. Just it is a small number, concrete number like 8, so like 27. So and 2 to the power 3, 8. So covering lemma allows us to push degenerate families from the restricted domains dynamically to the original domain uniformly with respect to the period, as long as the degeneration is sufficiently big. Okay, that is the outline, and this is exactly, so we produce a big vertical family on the original domain, and then we can justify in this way this philosophy that if the generation is big on some level, it is even big on the previous level, etc., and it gives a contradiction. And it works in the primitive case very well because of the entropy of on the Hubbard tree, which is important for the first step in my outline. Okay, So at that time, it was already a while ago, like 20 years ago, 2000s. And at that time, we moved further with Jeremy and proved, yeah, that theorem of Jeremy, so this argument works as I outlined. It works for bounded type combinatorics, bounded primitive type combinatorics. So a priori bounds for bounded primitive type combinatorics covered by Kahn's result. And we moved on to cover some unbounded but still primitive combinatorics. Namely, so what we required, so we have some family, arbitrary family of primitive combinatorics. So they are encoded by certain primitive Mandelbrot copies, and these copies should stay definite distance from the molecule of the Mandelbrot set. The molecule of the Mandelbrot set is everything that can be obtained from the main cardioid by the sequence of Dublin bifurcations, not Dublin, satellite bifurcations. That is the molecule of the Mandelbrot set, and we select copies. Primitive copies must be away from the molecule, of course, but we want them to be definitely away from the molecule. So, and if we consider all combinatorics of this time, then take infinity normalizable map with all these combinatorics, it will have quadratic-like a priori bounds. So the moduli fundamental annuli of quadratic-like normalizations will be uniformly bounded. From below, if we are talking about dynamical model. And interestingly, on the real line, if we restrict our to real parameters, infinitely normalizable real parameters, then this condition is satisfied for all combinatorics except the Dublin, which is satellite. Satellite is not covered. All primitive on the real line satisfies this condition. So we covered all points on the real line, so except those which involve, except the Feigenbaum point, most importantly, the most classical infinity normalizable parameter, the Feigenbaum parameter, was not covered by our old result. Okay, so then we proceeded to some other combinatorics, but at the moment it is kind of, it may look special, so let me skip it. It would not probably fit in my general slide today. So, but you see, so that sort of we covered general primitive, so and somehow covered a sort of definitely primitive, so to say, combinatorics. Not all primitive combinatorics, but still so good part of primitive combinatorics. But then satellite was not touched upon at all in this discussion. And then with Dima Dudko, we more recently, a few years ago, started to think more seriously about satellite case. And the first thing that, one thing that we did is actually fill in this gap for bounded combinatorics. For bounded combinatorics, we could sort of cover not only primitive types, but satellite types as well. And in particular, the Feigenbaum, classical Feigenbaum, which is on this picture, will be covered by our theory. And also these tripling bifurcations, satellite tripling bifurcations, when you go to the rabbit, through the rabbit bifurcations, and through the rabbit again, etc. This parameter was looked at in the old node by Hanin, Sinai, and Goldberg. There is one more name that I missed here, who numerically observed universality similar to Feigenbaum universality for these rabbit bifurcations and made the appropriate conjectures, normalization conjectures, but these conjectures were open until recently. So until this work with Dima. Okay, so yes, so the additional idea in this work to what Jeremy did is the following. First of all, it is a kind of on some philosophical level. So now in Jeremy's philosophy, we have to go from given level to the shallow level with bigger degeneration, then to the shallow level to bigger degeneration. And here we allow ourselves to go from a given level to a deeper level with much bigger degeneration. And then to a deeper level, it is alternative. So both ways will be possible, can appear. So we go to deeper level with much bigger degeneration, and then to deeper level with much bigger degeneration. And so if the first scenario fails, that what will happen is that the map must degenerate when we go deeper and deeper with super exponential rate. So degeneration will take over faster and faster and faster, super exponential rate. And it's actually not hard to show using some old idea by Dennis Sullivan of Teichmüller contraction. By renormalization, it's not hard to show that degeneration can happen only at exponential rate, and that is where the contradiction comes. Well, technically, it amounts to analyze certain to show this alternative that either we degenerate on the upper level, more degenerate on the upper level, or degenerate much more on the deeper level, and requires analyzing almost invariant horizontal arcs. The arcs for which cannot be covered like that by pullbacks of the original arcs, but such that it can be covered, it is aligned, almost aligned with the pullback of itself. And then the difference here must be extremely wide. And this is a rectangle which can be used to produce even bigger degeneration on some deeper level. So that is somehow very roughly some new idea which is needed to be added to Jeremy's strategy. So now with this, we have any bounded combinatoric satellite or primitive is good for quadratic-like renormalization. There are quadratic-like bounds for any bounded combinatorics. Okay, so let's now, we combined this result with our previous result with Jeremy and proof a priori bounds and MLC for all real parameter values. So it is a recent result, despite all the knowledge that we had about real line. So MLC still established recently, and the last point which was needed to do that is the Feigenbaum, the simplest combinatorial Feigenbaum point. Okay, and now let us go to the Siegel type situation, which is also, as I mentioned from the very beginning, it also fits into the normalization theorem in a nice way. So, but it would require sector-like renormalization. So somehow, what we wanted with Dima to do, so somehow there was this big part of primitive, and they stay away from the molecule. And so if we try to approach from other side, then the natural place to start is actually the main cardioid, which is, strictly speaking, is not renormalizable in the quadratic-like sense, but it is renormalizable in the sense of sector normalization, which could be relevant for the satellite renormalization. And so we can try to squeeze the set of parameters from both, so to surround the dark set of parameters from both sides. And that is what we started to do with Dima about 6-7 years ago, to try to understand geometry of on the main cardioid. And we were not the first who did this. So there was a great work of Ina Shishikura in the early 2000s, correct? Yeah, who proved a priori bounds, sector a priori bounds for the parabolic renormalization, and hence for small perturbations of parabolic renormalization. In particular, it worked for Siegel disks of sufficiently high type. And as it was mentioned already, it was important in the construction of the Julia sets of positive measure, for instance, by Duff and Sherita, and many other results. Essentially, neutral dynamics for high type renormalization was understood after that. For bounded type renormalization, for bounded type Siegel renormalization, actually it was also well understood because of Doedige's surgery. Doedige's surgery produces a definite geometric model for Siegel disks of bounded type, and it was very successfully used to understand bounded type Siegel disks. So Karsten did great work on that, so proving local connectivity of these Julia sets, measure zero, of these Julia sets, etc. But so essentially, we have control for bounded type. We have control for very high type. What is this dark area in the middle? And so what we looked with Dima together is to try to apply this near-degenerate regime, near-degenerate ideas to the understanding this type of renormalization. So Ina Shishikura's a priori bounds, they were based, as I mentioned, on understanding of parabolic renormalization. So it was, in a sense, perturbative method. So there is little chance to extend this perturbative method to arbitrary combinatorics. So let us try something else. And near-degenerate regime is good for arbitrary combinatorics. And so we actually indeed proved the sector a priori bounds for arbitrary combinatorics. The idea is the following. Start with bounded type Ziegel disks produced by Duodijis. Duodijis produced as well-controlled bounded type Ziegel disk. But certainly the geometry, so the boundary of the Ziegel disk is quasi-circle, so it's well-controlled geometry, so nice, but it is not uniform over combinatorics. It's not uniform. So what we wanted to get uniform bounds on bounded type Ziegel disks, with arbitrary combinatorics, uniform bounds. And the way to do that was somehow to upgrade non-uniform bounds given by Duodijis to uniform bounds in some way. So what we did as a strategy is the following. So we again assume that there is some degeneration. We should consider modulo of certain rectangles. So start with some combinatorial interval on the Ziegel disk and consider rectangles that go from this combinatorial interval sufficiently far away combinatorially, like that. And we want to bound this type of moduli from above. Assume that it does not happen. Assume that they degenerate. And then, so we use cover and lemma and much more machinery, so to produce much bigger degeneration on the next level, or slightly definitely bigger, twice bigger degeneration on the deeper level. And then again, we can consider if we pass certain threshold, which is absolute threshold. Threshold should not depend on combinatorics. There is an absolute threshold such that if there is degeneration, this absolute degeneration on certain levels, and there is even bigger degeneration on the next level, and then there is a bigger degeneration on the next level, etc., etc. But altogether, our Ziegel disk has bounded geometry, non-uniformly bounded, but bounded. And in this way, we will beat any bound on the geometry. We'll beat, and this will be a contradiction. So how exactly it is done, I don't have time to say, because, well, even maybe even on the level of rough outline, because my time is almost up. But let me make one more important remark, that we should be careful with Ziegel disks because they do degenerate. Ziegel disks which are close to parabolic points of high type, which is close to parabolic points, they are amoebas, which is a kind of close to the flowers, to the parabolic flowers. And for such amoebas, there is some degeneration. There is white rectangles in between two legs of these amoebas, So we cannot just hope to get some naive a priori bounds for all Ziegel disks. So the bound should be slightly less naive. Namely, once we see some rectangle like this, wide rectangle like that, then we should just cut it off. We should just fill in this field and regularize our amoeba by some more regular on this scale, more regular disk, which will not be completely invariant, but which will be almost invariant up to return time, up to associated return time. And this can be done from level to level, starting with deep levels and proceeding up and up and up from level to level. It can be done inductively. So in the end, so we produce on the top level some quasi-disk, some actual quasi-disk with uniformly bounded geometry, which contains the original Ziegel disk. So, and which is to which the restriction of our map is injective. And one of the immediate consequences of this analysis is construction of so-called mother hedgehogs. So hedgehogs are local objects constructed long ago by Peretz-Marka, and they were very efficient, very good for understanding of local dynamics of Kramer points. But in order to capture critical points, we want to have a hedgehog which extends all the way to the critical point. And that is what our theory immediately produces. So this mother hedgehog is invariant, so compact, full, connected set, which contains both the Siegel fixed point and the critical point. So it controls, it is somehow homeomorphic control of the behavior, rotational control of the behavior of the critical point. And now it is not only for Siegel disks, but it is also for Kramer points, because once we have uniform a priori bounds for Siegel disks, then we can pass to limits and can get control of Kramer points as well. But it is only the first step. We are very optimistic that the whole theory, which was developed in the near parabolic regime, which was based on Inoue-Shishikura results, can now be carried for arbitrary rotation numbers. We are now discussing this with the authors of the near parabolic theory, Shishikura, Fei-Yang, and Wood-Shiragi. For instance, they classified all types of mother hedgehogs depending explicitly on the arithmetic of the rotation number, Hermann, Bruno, etc. So there is a trichotomy how these mother hedgehogs can be classified. Or there is a conjecture by Stefano Marmi with Yakos and Moussa, which was in near-degenerate regime proved by Arnaud and Davout, and now I think that there is a chance to extend it also to arbitrary combinatorics. But it is a matter of some further checking up, but it seems that it is quite feasible, that it's possible to do. And so I am 3 minutes over. Let me take 1 more minute just about some dreams, which are a little bit more now than dreams at the moment. It is work in progress that we are doing now. With Dima, we are trying to apply now these ideas to satellite case, now unbounded satellite case, and applying these ideas to control uniform a priori bounds on sector normalization. For satellite, we do know that quadratic-like normalizations fail. Sector normalizations is what has a chance. And so we want to control. And this control, it seems, and so we are quite optimistic looking at this issue now. That seems that this machinery that was developed on neutral normalization, this near-degenerate regime machinery, can be applied to satellite case. And in particular, part of the machinery would be regularization of the renormalization flowers to certain almost invariant rotational domains. So somehow, if there is some degeneration of this kind, then we can regularize and obtain an almost invariant disk, and then Siegel machinery all of a sudden becomes tremendously relevant to this situation, essentially can be used as a black box. So, but it is work in progress. Certainly, I'm not claiming at this moment any definitive results on this problem. But so that is where we stand, as I can tell. Okay, thank you.
Thank you. There are comments, questions?
People are escaping.
So when you have a mixed type of primitive and satellite type renormalizations, so both sides you have a priori bound in terms of modulus of annuli, and can you transfer from one side to another?
So in general, I would not say anything, but in bounded type we have quadratic-like priori bounds, so we can do this in general. This should be given a thought. So how to switch? It will be a kind of, so if we are able to deal with the satellite case, this will be the final problem how to merge them together. I think that sector normalization will be more fundamental. So somehow sector normalization should work in this gap regime. So almost satellite regime, sector normalization should work, and then the sector normalization in the gap regime hopefully can be promoted to the quadratic-like normalization in the primitive case.
I see.
In the primitive case. Yeah. So,
thank you.
Thank you for the great talk. Just a very basic question. When if you proved a priori bound for the satellite, any kind of satellite, this implies MLC at those parameters, or there is another condition?
So, so MLC would follow, but it is also something. There is no conditional theorem saying that once we have the sector normalizations for satellites, that we can immediately go to rigidity. But it is quite clear that it should be doable problem. So we are now worried. We are busy with a priori bounds. So, but if we get a priori bounds, it seems that it should be easier problem to go to rigidity from a priori bounds. Because once you have uniform control in all scales, that is what quasi-conformal maps are all about. So quasi-conformal maps are about uniform rough control in all scales. And so that is what a priori bounds give us. So it should be possible to argue in favor of quasi-conformality of the conjugacies. Rigidity problem is the problem of quasi-conformality of the conjugacy, and it should be doable problem. So, but I'm an optimist.
I have two questions. So first question, so you mentioned Hanin-Sinai conjecture. So what was their motivation to ask this question? Because it's not what you see in Rios, this tripling bifurcation. And the second question, I mean, still, do you believe maybe after all this development that there will be kind of a meta theorem saying, well, given a priori bounds, in some form you can get rigidity?
Well, I think that in the end of the day, it should be such a meta theory, but I think that it will be already irrelevant because it will come at the time when we know exactly what kind of a priori bounds we have. We should know exactly first what kind of a priori bounds we have, and then pass, and then it can be formulated probably as a conditional result. So it is. And about Hanin, Goldberg and Sinai, so well, it was time when the Feigenbaum normalization was extremely popular on one hand. It is early 80s, it's very, very early. Feigenbaum was a hot topic at that time, and Mandelbrot set was another hot topic. They just looked at these two things together. So just looked at the bifurcations. So tripling rather than doublings, and so, and for them it was very natural to look from the normalization point of view. The whole Sinai school looking at the things from normalization point of view. So they looked at the picture. They looked at the picture and made conjectures. No, it's numerical. It's a note, 2 pages note. They just drew a picture, calculate this scaling factor, unstable eigenvalue for the normalization, make conjectures, and that's it. So, but it's kind of inspiring.
Okay, other questions or comments?
So yeah, I guess so. I'm the last speaker.
Yes, you are.
It is my duty and pleasure to thank the organizers, Anna, Nuri, and all the organizers for this wonderful event and this wonderful time for all of us here. Thank you.
I have more people to thank. So thank you, Misha, for being here. I'm so honored and happy to have you here. Thank you all for being here. As the same Mexico, it's the people who make the party. And well, of course, I need to thank the Centro De Giorgi and Monica and Federica for taking care of so many aspects of the conference. And I really want to thank the other organizers, especially Vas, who unfortunately could not come here, Nuria and Carlo, who had to leave right now, but whenever there was a problem, I knew I could text them, and in a few minutes, they would help me solve it. And I really, really would like to thank Carlo Carminati and Stefano Marmi for the financial support for this conference, especially Stefano Marmi. Without them, this conference would not be possible. And let me know, at some point when we exploded from 50 to almost 80 people, it was clear that we don't have enough money, and I added some more money. And I was ready to cancel the coffee breaks, okay? So I would like to make an applause to all of you, and especially Carlo, Stefano, the other organizers.